Good morning, Katie.
Good morning.
Good morning, Angeles.
Good morning.
Good morning. Good morning, Kristen.
Good morning.
Okay, guys. Good morning, welcome. And
Morning.
okay. And before I start, or I can say continue, any questions? Any questions about it? Okay, what we discussed yesterday.
No.
Okay.
No.
So you guys are good on the relationship so far? Huh?
So far, so good.
So far, so good. Okay, that's always something. Okay, guys. And good with the units too?
Yep.
Okay. So we were at our acoustic variable, right? Okay. We already said one was pressure, which mathematically was equal to force over area. Here, okay. The unit could be okay either Pascal or mainly okay used by our formula here. Newtons, or we can say it's okay centimeters square. The other variable is our density, which we mainly said was going to be as okay mass over volume. Okay, so we can say it's okay. The unit should be any unit of mass. We can say it's okay kilogram or liter, for instance. And or yes, okay. This liter could be yes, okay, any unit of distance cubed. Or last acoustic variable. Although yes, okay, the book only mentions distance. Or what they actually is okay mean by this distance here is going to be, we can say okay, distance of particle motion. Okay. And as far as distance is concerned, guys, well, okay, yes, when we talk distance, we talk length, it means, okay, that's going to be using any unit of distance or length, so it could be a meter. We can say it's okay, a centimeter. We can say millimeter. You can say micrometer, and so on. Okay. Because what we mainly as okay concentrated our discussion upon yesterday was saying that okay, yes, we have a particle. And that particle is going to be moving back and forth. Okay. Mainly cheers, okay, cause the sound wave try to move in this direction. If our source was here, or let's say it's okay in this direction, if the source was here. Right? Okay. So mainly as okay, just the measurement of as okay, the movement or the distance that this particle moves. That's mainly as okay what they talk about. Okay, guys. So these were your three acoustic variables. Okay, so pressure, density, and distance or distance of particle motion. Okay. These were the units of each of those parameters. No, variable, sorry. Any question? Oh, that's okay, yeah. Yeah, done. Any questions?
So for distance, there's no relationship that we're.
No.
Okay.
Because my dear, here it's okay. There's no formula for it.
Right. I just want to make sure.
It just said, well, okay, listen, this particle, that's okay if it moves, let's say it's okay 1 millimeter. That's it.
Sounds good. Thank you.
Yeah. Okay. You will only as okay have a relationship is okay as if a parameter, for instance, or a variable is going to as okay can be calculated by as okay multiple or different factors. Did that make sense? Okay.
Yep.
So for this one here, it's okay. There's no real relationship. So you want to put it that way. Okay. Now, the next thing that okay, as the chapter is okay talks about or mentions is going to be is okay what we'll call the acoustic parameters. And just like it's okay, there are 7 oceans, 7 continents, 7 days in a week, 7 levels of heaven and 7 levels of hell. Likewise, as okay, are there 7 acoustic parameters. Okay. Now, guys, we're going to have okay as a detailed account of these 7 acoustic parameters here is okay in chapter number 3. Well, as a matter of fact, it's okay what chapter number 3 is all about is talking about your 7 acoustic parameters. Okay. But since that's okay, dimension here, we can just briefly, just for okay, yes, give each of them is okay, 1 minute to talk about. So we can say, okay, the first one is going to be a period. Now, period, guys, that's going to be okay, something that will measure time. Time of a certain event to be completed. So the period is going to be as okay, the time or one cycle, or we can say it's okay, one wave of sound to complete. So if you, for instance, okay, take one cycle or one sound wave like this, what the period mean is going to be as okay, how much time does it take for the sound wave to start and finish? That time measure is going to be as okay, referred to as the period of the sound wave. Okay, so we can mean it as okay, the time for one cycle or one wave to complete is going to be as okay, what we call the period. Okay, now since it is a measurement of okay, yes, time, it's going to yes, okay, be expressed in a unit of time. So what will be a unit of time? Second. You can go with multiples of seconds, you can go with fractions of seconds. But no matter what, yes, okay, your period is always going to be expressed using any unit of time. Is that clear?
Yep.
Yep.
Good. Okay. Now the next is what we'll call, yes, okay, a frequency. Now, guys, generally, yes, okay, if you look at the word frequency, what will come to your mind? Generally speaking, please don't go to sound waves and things like that right now. If you understand, yes, okay, what it means in general terms, you can always, yes, okay, use or refer that to sound waves as well. But generally, it's okay, what do you mean by frequency?
Like how often something happens.
Exactly. How often is it that something happens? Right? Okay. Yeah. Okay. So now we're gonna say that's okay. How often is that okay as a sound wave is being produced in a unit of time? So that's going to be the frequency. Clear? Okay. So what would it be now? We can say that's okay. Okay, let me just write it out. Yes. The number of sound waves. Please keep in mind, guys, okay, the sound wave is okay, the term wave maybe is okay, replaced by cycles. Okay, so number of sound waves or cycles completed in a unit of time is going to be the frequency. Now, mainly as okay, guys, to keep yes, okay, to keep it fixed. As okay, be able to just okay understand what we mean by frequency. This unit of time has made as okay, kept constant as a second. Okay, so generally as okay, you could say as okay, the number of times a event occurs in a span of time is going to be as okay, the frequency of that event. But when we talk about it in terms of sound wave, we mainly says okay, the number of cycles. Of a sound wave, that's okay, completed in a second. So let us just say that okay, at this period here, for instance, yes, okay, measured 1 second. And what we can see is that we have okay, yes, one cycle completed. There's another cycle completed. We had another cycle completed, all right. We had another cycle completed, and we had another cycle completed. So in this case, yes, okay, what we see is that we had a total of 4 cycles completed in a second, right? Okay. Okay. Now this frequency as okay can be as okay written in 2 ways. You can either say that we had 4 cycles per second. Did that make sense?
Yes.
Good. Or this cycles per second here, this term here that says, okay, cycles per second can actually, as okay, be replaced by hertz. So we can also say as okay that the frequency could be 4 hertz. Did you guys get that?
Yep.
So yes, okay, cycles of sound wave, yes, okay, completed in a second is going to be, yes, okay, the frequency of that sound wave. Okay. Yeah, okay. So just in this example here, it's okay, we said this was measuring time of 1 second, in which we had, let's say, it's okay, 4 cycles. So our frequency, yes, okay, was either 4 cycles per second or 4 hertz. Yep. Any doubts so far? Yeah, okay. Okay. And guys, please mind, this is only an intro. Okay, this is only an intro. The relationship, the further details, blah, blah, blee, blee, blue, blue. Yes, okay, that will be discussed in chapter 3. Clear? Okay. Unless you guys want it now. Then we may be stuck in this chapter here. It's okay for the rest of the week. Okay. Let's go with the intro. Let's be easy on you guys, okay? Okay. Now, usually that's okay what I do, and okay, as you will see me doing that is okay when in chapter 3. I will skip, yes, okay, the next 3, yes, okay, what the hell you call it? Parameters. Because, okay, we already said, yes, okay, period. We already said, okay, yes, frequency. And now, yes, okay, coach, yes, okay, what we call the wavelength. Now, let us just put it this way and say, yes, okay, this here is okay, was a sound wave, right? Okay. This was one complete cycle of a sound wave. Yep, okay. Where we says, okay, if we measure this in terms of time, that will be, yes, okay, what we call the period. Yeah, okay. We may say that, okay, yes, we have, okay, yes, an XYZ number of sound waves in a time span of 1 second. So yes, okay. The number of the sound waves that we had in that second was the frequency. Yeah, okay. Just like yes, okay, we're going to have yes, okay, have cycle or a sound wave. So we have a wave. Or when we yes, okay, measure the distance from here to here of this wavelength, of this wave here or cycle, that is going to be yes, okay, the wavelength. So pretty much okay, what is the length of the wave? Clear? But please, guys, keep in mind that that's going to be okay, being from the start of the wave to the end of the wave. This distance here is okay. When we measure from this point to this point here in distance, using a unit of distance, we can say it's okay, centimeters, we can say it's okay in millimeters, we can say it's okay in micrometers, you can even go meters and so on, so on, so if you want to. Clear? Okay. But this distance here is okay, that distance or length is going to be as okay referred to as the wavelength. Did you guys get that?
Yep.
Any questions? You can mainly as okay, just look at it in this way and say, this is the length. Let's say it's okay, you are giving it's okay a chance to run a certain distance. Okay. The track that they provide you with, they will say, okay, this is the length of the track. Clear? So that will be the wavelength. Then they will say, well, okay, yes, how much time will it take you to make, you can say, okay, one round around that track? That will be the period. Clear? Okay. But then if they say, yes, okay, how many rounds around this track can you make in an hour, for instance? Okay. That will be the frequency. Did that make any sense? Okay. So already from here, yes, okay, some of you, yes, okay, should be able to figure out the relationship that these things here have. Because these three fellows here are going to, yes, okay, be related in one way or the other. But let me not bother you guys with that yet. Yeah, okay. So what was the period? The time that it takes for one cycle or one wave of a sound wave to complete. What was the frequency? How many cycles? How many waves did a sound wave produce in a period of time? So in this case, yes, okay, we will keep the period of time a second. Clear? Last is okay, yes, physically. How long is the wave from the beginning of the wave to the end of the wave? Or one cycle. What is the physical measurement of it? That's going to be its wavelength. So media is okay, just the length of the wave. But here is okay, please keep in mind that okay, length is not in terms of time, but in terms of physical length. Or what you measure, right? Okay. Okay. The time length of yes, okay, the wave that is going to be is okay, what we call the period. Did you guys get that? Good. Now, guys, yes, okay, we have another parameter. And we call that one, yes, okay, the propagation speed. Okay, that's okay. As I said yesterday, propagation is okay. It does mean it's okay, just a fancy word for progressing. Or we can say it's okay, moving on, right? The actual word here is speed, which means it's okay, just the term is always mean it's okay, it's going to be all about it's okay, how fast or slow. Clear? Okay. So in terms of yes, okay, your sound wave, when we talk about yes, okay, propagation speed, that's mean yes, okay, it's going to be yes, okay, how fast, or let's say slow, is it that a sound wave travels? Did you guys get that?
Yep.
Yep.
Good. And I think yes, okay, the first day I talked about yes, okay, what would make your speed. Okay, so the unit for speed is mean yes, okay, there's going to be the unit of propagation speed here as well. Propagation is just okay, as again, it's like a fancy word that they popped in here is okay, mainly it's okay, just to talk about it's okay, specify it's okay what we're talking about. The speed at which okay as the sound is traveling ahead. Okay, but the unit for speed is going to be as okay, any unit of distance divided by a per time or unit of time. So as long as you take any unit of distance, which could be as okay, meter, a fraction of meter, or a multiple of meter, yes, okay, you'll be good. And as long as okay, as for time you use, yes, okay, any use, okay, yes, okay, we can say second, but yes, okay, you can talk about a fraction of a second, you can use a multiple of a second. Okay. But this, yes, okay, is how, yes, okay, the unit of speed is made up. So the propagation speed is just going to be as okay, how fast or slow is it that a sound wave is traveling. And I already gave you guys, that's okay, a little tip about that thing. Okay. Because your speed of sound is going to be as okay, determined by the medium. Clear. So we said, okay, it travels fastest in solids, slower in liquids, and slowest in gases. Clear. Okay, so that's going to be as okay, you can say as okay, the propagation speed is going to be highest in solids, lower in liquids, and lowest in gases. So the propagation is nothing else but just how fast or slow is it that the sound travels through or travels. Okay. And what we will see, is that that's going to be something that will be determined by your medium. Did you guys get that? Okay. So just like, how fast can you make your car run or ride or drive or whatever? That's going to be the speed. Okay. So propagation speed is nothing but the speed of the sound. Any questions yet? Nope.
I have one, sorry.
Go
So
ahead, Medina.
would that mean that propagation speed and medium are inversely related? Or
No, my dear. Okay. What I said was that, I already mentioned that, yes, propagation speed of sound. Because what is the propagation speed? That is, the speed of how fast or slow the sound will travel. Clear? Okay. But what I said earlier in this chapter here was there was going to be fastest in solids. So a sound is in terms of physics is going to travel fastest in solids. What is solid? Wood, for instance. Okay, yes. Your wall, a brick, and things like that. Okay. Whereas, yes, is going to be slower. Or we can say it's slow in liquids. What's liquids? Tea, coffee, water, juice, blood, urine. Clear?
okay.
And
Yeah,
it's going to be slowest in gases. What is gases? Air. So what can we say here? It's in solids, we have the greatest propagation speed. Whereas, as in gases or in air, we have the lowest propagation speed. Whereas, as in liquids, is going to be, sometimes, in between the speed of sound in solids, less than that in solids, but just greater than that in gases. Clear? Okay. So it's going to be determined by which medium. Determined by the medium through which the sound travels. Okay, that will determine is going to be faster, slower, or slower. Did that answer your question?
yes, thank you.
Okay, no problem. Okay, so you can't say that it's inversely proportional to the medium because in some medium it's in some medium it will go and in some it will be slower. Okay, so it'll be the nature of the medium that will determine the speed of sound. Okay, what are the three natures of medium? Especially as okay for sound, solids, liquids, and gases. Okay, because yes, okay, these were the only three mediums through which yes, okay, sound could travel. Because these are three mediums or forms of a medium which we have particles that can move. And since we don't have particles in a vacuum, that's why it's okay, sound. Couldn't travel in a vacuum. Okay. As I was sitting in a vacuum chamber and it's okay, trying to convey, yes, okay, the words to you, it will be like this. Did that make sense? Okay, guys. So that's your propagation speed. Okay. How fast is it that the, yes, okay, sound reaches you after they have been uttered? Now, does anybody know, yes, okay, which form of energy may travel fastest?
Light.
Light.
Light. So, sound is relatively slower than light. Have you wondered why? If there's lightning, you first see the spark and then, okay, yes, a couple of seconds later, that's when you start hearing the booming. There's lightning. You first see the spark of lightning and, okay, yes, later on comes the boom. We just said it. Because light travels faster than sound. Did that make any sense? So everything that happens around us is just okay in one way or the other physics. We just don't think about it that way. Okay, guys. Bear with me. Good. Then, guys, okay, yes, the next three, yes, okay, parameters, which we'll say is going to be power, intensity, and amplitude. Okay, guys. Now, what these three parameters here are going to be. These three, yes, okay, together are going to be called the bigness parameters. Now, the reason that we call them the bigness parameters is mainly, yes, oh, shit, sorry. is mainly as okay because these are going to be as okay the parameters that will determine as okay the size or the bigness of the sound wave. Now, what power mainly is going to be here is okay. Power is mainly going to be as okay, just a measurement of, because of the rate of transfer of energy. That's going to be the power. Okay, so what this fellow here is okay, mainly is okay, concentrates upon is how much energy is being used. Well, let's not say used, let's say it's okay, being carried. You can, in this case, it's okay by our in case of sound, it's okay by the sound wave. That is going to is okay determine, well, that's going to be the power of the energy. But it's all here, it's okay, how much energy does the sound wave carry? Did that make sense?
Yep.
Good. Whereas, guys, intensity is going to be as okay the concentration of, let's do it this way, power over area. Where you mainly can say is okay, in whatever area we have, how much energy is fitted into that area. That is going to be as okay, the intensity of that sound wave. So again, it's okay, the intensity is again, it's okay, just a term of okay, yes, measuring as okay, how much energy is it that the sound wave carries. Did you guys get that? Where guys, when we look at the amplitude, now doesn't mean that's okay, Joy, going to be, this is a more of okay, yes, a physical size of the beam. In our case, here, it's okay, it's going to be, it's okay, the sound wave. So we can say it's okay, we may have, it's okay, two sound waves. Now just let us put it this way and say it's okay. If we had a greater power, we most likely also will have okay as a greater intensity. And what that greater power or greater intensity, mainly because okay, it's going to be more energy carried by the sound wave is going to produce a wave with a big amplitude. Whereas, guys, on the other hand, if we had a sound wave with lesser power, if we had a sound wave with lesser power, it's most likely going to have okay, a lesser intensity. and it's going to, yes, okay, produce a sound wave with a smaller amplitude, lesser amplitude. Now, guys, please keep in mind, because, okay, people confuse amplitude with wavelength. And that's why I said, okay, I tried to, but let me just get it more better with my artistic skills. Because it's okay, this is going to be okay, our sound wave with a big amplitude. This is going to be a sound wave with a smaller amplitude. Okay. Yeah, please, guys, remember that the measurement from here to here in terms of time was what we call period. In terms of distance or length, or what we call wavelength. Yeah. Okay. So what do you get from that? That you can have two waves, for instance, with the same period and or the same wavelength, but different amplitudes. Where we can say, okay, the amplitude for our red wave is big, and or that from the for your green wave is small amplitudes. Did you guys get that?
Yep.
Yeah, okay. Why it's okay. What is the amplitude going to be related to? Pretty much, okay, yes. How much energy is it that, okay, yes, the sound wave will carry? Now, unfortunately, it's okay, we can't physically see the sound waves. Okay, it's not that, okay, yes, I uttered the words coming out of my mouth and you see them as, okay, flying in the air. And you try, okay, let me just catch all this and pop it in my ears. That's not how it works, right? Okay, so let's just use an example, yes, okay, where you, yes, okay, may be able to, yes, okay, see the waves. Big waves, small waves. If you can say, okay, big waves will be, yes, okay, waves with a bigger amplitude. Waves with a smaller, yes, okay, smaller waves are going to be, yes, okay, waves with a smaller amplitude. But it's going to be determined upon, yes, okay, it's going to demonstrate, yes, okay, the amount of energy that produces these waves. Have any of you ever been to an ocean or a beach or just a little river or stream? Now you may see that, okay, yes, even though it's an ocean, no waves. And you say, it's okay, it's a nice hard day, it's a day to hit the beach. Because, okay, there's no air. Not to talk about, it's okay, when you have a hurricane or it's okay, storm coming by. What's a storm? What makes a storm a storm?
thunder, lightning, and rain.
Okay. You don't have to have rain to have a storm.
Wind?
Wind. What kind of wind?
High speed.
Or strong wind, right? Or more correctly says, okay, a lot of wind energy. Or we can say, okay, that air is carrying a lot of energy. And how is that going to just, okay, affect what you see in the ocean or sea? It's going to produce big waves, right? And those big waves are going to be waves of a great amplitude. Now, guys, that's the easiest way that I can explain this. So you can say it's okay, more power, a stronger intensity wind, greater amplitude of waves. Clear? Okay. Less energy of the air, less intensity. Less intensity is okay, is lesser amplitude of the waves. Did that make any sense? Clear? Okay. So both intensity and that's okay, and power. I mean, that's okay, just going to, because it's okay, numerical measurements of how much energy is it that the sound wave carries. Whereas amplitude is just going to be, okay, how big, how small is it that this sound wave here is going to be. Did you guys get that?
Yes.
Yeah, okay. Now please, 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 please do not confuse amplitude with wavelength. Clear? Because you can have a small, you can have a wave with a, we can say, okay, low amplitude, but the hell of a wavelength. Whereas, okay, likewise, you can also, okay, have a wave with a big amplitude. But it's okay, then you see it's okay, shorter wavelength. Did that make sense? Or you could have, yes, okay, two waves with the same wavelength, but different amplitudes. Did that make any sense? Good. Any questions now? Okay, guys, so just chew a little bit upon, yes, okay, your amplitude. Okay? Chew upon the amplitude a little bit. Because that's going to just, okay, where we'll get handy in our next topic, which is going to be interference. So I'm going to give you guys just okay 15 minutes to just okay do your fresh ups or whatever's, and um just okay think a little bit about amplitude. Yeah, okay. Because that's what we're going to be okay use for our next topic. But before I send you guys off, any questions? Anything that I said so far that just passed on top of your heads? No. Everything clear so far? Okay, guys, so think of amplitude a little bit, okay? So I will see you guys at, should we say 10:15? Okay, guys, welcome back. Have you guys been chewing on your amplitude? Chewing on the amplitude. Okay. Okay, now just a little bit, yes, okay, we can say it's okay, last jumping around. And that's why it's okay, what I want to do first is well, let's do it this way. Let's say that we take a sound wave. So we can say it's okay, diagrammatically it's okay, this is how we may draw what will be referred to as a sound wave. This is one cycle. Okay. Now what we see here is that, okay, yes, this cycle here has a top point. This part here is going to be known as a peak. Just like the peak of the mountain. So pretty much, okay, yes, self-explanatory. We can see it's okay, this lowest point here, that's going to be referred to as a trough. Yeah, okay. So what a sound wave or what one cycle is going to have a peak and it's going to have a trough. Did you guys get that?
Yeah.
What we mainly as okay can say here is that okay, yes, the measurement from here to here along this line here is what we call the wavelength. Here. Whereas or maybe from here to the peak or from here to the trough is going to be the amplitude. Did you guys get that?
So from highest point to lowest point is the amplitude?
No, not necessarily. Because, okay, we have this, what we can call this, okay, center line here, or average line. Okay, so this here is going to be as, okay, the amplitude. And or this here is going to be the amplitude. Okay, we'll get to this in the next chapter. Okay,
Okay.
but one thing that I just want to say is, okay, that the highest point of a wave that's going to be referred to as the peak. Whereas, okay, as the lowest point of a wave is going to be known as a trough. Did you guys get that?
Yeah.
Now, let's talk of what we call interference. Now, guys, before getting into, yes, okay, the theoretical interference, what do you think interference is? Generally, yes, okay, just in the regular English language.
It's when something is interrupted, like
Okay, let's say that, okay, as I'm speaking, or anybody is trying to speak, and somebody else goes in and say, "Bop, bop, 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 beep, 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 bop, bop." Okay, what is that going to be? He or she is, okay, just interfere the speaker. Okay, either by trying to, yes, okay, bring in his or her opinion, or yes, okay, not even yes, okay, bringing in an opinion is, okay, just making crazy baby noises, right? Whatsoever. Yeah, okay. Okay, so what we will need for interference, one thing that would be needed for interference is two, oops, shit. Sorry. Okay. All we can say is, okay, more than two sounds travel in a medium. Yeah, okay. So we can say it's okay, we have any medium. Yeah, okay. Okay. Now, if there was only one sound traveling through this medium, yes, okay, that will mean, okay, there was only, yes, okay, one sound wave. That will mean, yes, okay, mean that there will be, yes, okay, no interference. So one thing that is must for us, okay, interference to occur is that we have to have at least two sound waves traveling in the medium. Yeah, okay, two or more. So there's really no, yes, okay, there's really no upper number of how many sound waves can travel for a medium where you say, okay, this is not interference anymore. Did that make sense? Okay, so for interference to occur, what do we need? At least two sound waves to be traveling through a medium. Because it says, okay, this one here is okay, was the first sound wave. In this case, it's okay, there's no interference. Right? Okay. Did that make sense?
Yeah.
Yep.
Good. So What will happen to, that's okay, what is going to be must for interference to occur? We will have, okay, so we will need another sound wave to be traveling in this medium here. Okay, good. That's where we have it. Clear? Okay. So now do we have, yes, okay, two sound waves traveling in me. We have a blue sound wave, we have a green sound wave. Did you guys get that?
Yep.
Yeah.
Good. And what's going to mean by interference is that, okay, we can take any point. We say it's okay. No, let's choose a color that's going to be standing out. We can say it's okay at this point here. These 2 points, yes, okay. Or even, yes, okay, at this point here. Or let's say it's even at this point here. Or at this point here. Or at any point. But what did we see that, okay, yes, these 2 sound waves here is okay. Okay, yes. Or what actually is okay happens when these 2 sound waves, okay, meets a specific point in time. That's when it's okay, interference is going to happen. Is that clear? So interference is mean that's okay, is going to be as okay the, you can say okay, some sort of, it's okay. It's okay. Even that's going to happen, yes, okay, when 2 or more than 2 sound waves, that's okay, reaches a specific location at a specific time. Okay. But you can have interference here, you can have interference here. Okay, between, yes, okay, the green and blue wave. Did you guys get that? Okay, so pretty
Yes.
much, okay, what happens, we can say, okay, due to 2 sound waves traveling in a medium that reaches, okay, at a certain point at a specific time is going to, yes, okay, be what we will call interference. Did you guys get that?
Yep.
Now, guys, let's just see. Let's say that this here is okay, is the medium. And okay, let's say it's okay. So the next thing that we will be talking about is going to be as okay. We may have something that we'll call in phase waves. And we will have something that we will call out phase waves. Okay. Now, if we say that waves are in phase, let's just say it's okay, we have 2 waves in this case here, or 2 sound waves. One is a red sound wave, right? Yeah, okay. So this is mainly as okay, just 2 cycles of a red sound wave. Okay. Now, we may have another sound wave which is going to be as okay in phase with this red wave here, and that's going to be as okay a green wave, for instance. These 2 waves here are in phase. And why do we call them in phase? And this is where it's okay, things such as okay, as your peaks and troughs comes into action. Because we can say it's okay that the red and green wave, they had their peaks at the same time. And if you look, it's okay, they had their troughs at the same time. Even here, it's okay, they both had their peaks at the same time and they had their troughs at the same time. Did you guys get that? So in this case here, it's okay, we can mainly say it's okay that the green and red waves are in phase sound waves. Did you guys get that? Right. Now, if you have ever seen okay soldiers marching, have any of you ever seen or heard soldiers marching? Okay. And if you look at it, okay, if you listen to their footsteps, what does it sound like? That they all okay hit the ground at the same time, right? Okay. That's why it's okay you hear all these footsteps as one big loud sound. Yeah, okay. But you can mainly say, okay, since they hit the ground at the same time with their feet, they are in phase. Or their steps are in phase. Or you can say, okay, more synchronized. Did you guys get that? Okay. But what does it mean to be as okay in phases? That okay as when sound waves is okay, pretty much okay as will have their peaks at the same time or troughs at the same time. Or we can actually say it's okay. The most likely is okay will have is okay either same periods or wavelengths. They can be of different amplitudes, but it's okay, they have similar periods or wavelengths. Whether that was 2 sound waves or 3 or 4 or 5. I just chose to go with 2 because it's going to be easiest, okay, just to draw. Clear, okay. But if you guys want to, yes, okay, you can put as many sound waves in here as you want to. Okay. With different amplitudes. Okay. But it's okay if those sound waves, that's okay, still have okay, yes, their peaks at the same time and the troughs at the same time, yes, okay, they will be in phase. Did you guys get that?
Yeah.
Okay, sorry guys. I guess my waves got a little bit too big. So let's just go on to another slide and talk a bit about what it means to be out phase. And as a matter of fact, it's okay. I may it's okay just draw 2 examples of out phase waves. Now again, yes, okay, we can still say it's okay that we're going to have okay as a red sound wave Okay, and we may have as a green opposition, sorry. A green sound wave for both examples. But that's okay. This is going to be, they're going to be our phase. So what we see is that, let's just say it's okay that we had the red wave. This is the red wave. And we may say it's okay the green wave. Now what do you see? Well, we can mainly say that, okay, yes, this is, oh shit, sorry. This is where we had the, okay, no. This is where they had their peaks, right? And likewise, we can say, okay, this is where they all both had their troughs. So the peaks of the red and green waves, that's okay, it happens at different times. The troughs happen at different times. So that pretty much, okay, just makes them our phase. Did that make sense?
Yep.
Okay, so this is one example of, you can say, as okay being our phase. We can also take an example like this. And again, yes, okay, we have the red wave. This is our red wave. And this is going to be, okay, our green wave. So what do we see here? We can, yes, okay, we sure to say that, okay, yes, when the red wave had its peak, that was when the green wave has its trough. When the green wave has its peak, that was when the red wave has its trough, and so on. Yeah, okay, so this one here is also going to be, it's okay, out phase. Okay, so both example A and or example B are examples of waves being out phase. Whereas what we see here, sorry, is in phase. Did you guys get that?
Yes.
So what is it that we are going to do now? Now both in-phase waves can interfere. And so can out-phase waves. Clear? Right? What did we say that was, yes, okay, the minimum requirement for interference to occur? 2 or more than 2 sound waves traveling in a medium, right? Clear? Okay. Once we have 2 or more than 2 sound waves, that's okay, traveling in the medium. Well, okay, yes, you will have interference. Okay, But that interference is going to be as okay, or the type of interference is going to be determined whether these waves here are in phase or out phase. Did that make sense?
I have a quick question.
Yes, my dear.
So if you have a wave that has like multiple sound waves, like let's say there's three, is it possible that like two could be in phase and the third one could be out phase at the same time?
It could be.
Okay.
Yeah, okay. So as far as interferences are concerned, we mainly as okay are going to have two types of interference. Now that's going to be as okay. One is going to be as okay what we will call constructive interference. Clear? And the other type is going to be as okay what we will call destructive interference. Yeah, okay. Now, guys, what did we need for SOK interference to occur? You can say it's okay, at least two sound waves, right? Okay. Right. But constructive interference is only going to happen, yes, okay, when the sound waves are in phase. So whichever sound waves or how many sound waves we have, for them to, yes, okay, constructively interfere, mainly requires that these sound waves here are going to be in phase. Did you guys get that?
Yep.
Where, okay, yes, that just leads us to, yes, okay, the next question about, yes, okay, what about destructive interference? Now, destructive interference is mainly, yes, okay, going to be, yes, okay, seen when the sound waves are out phase. Here. Now, the main thing about is okay, the type of interference actually is okay lies in the word or the name of the type of interference. Constructive and destructive. So guys, when I say constructive, what does that mean?
Formation, building.
Making up something, right? Or you can say putting things together, right? Yeah. Okay. If I give you, okay, a box of building blocks and say, yes, okay, play with this. What are the two games that you can play? You can either, yes, okay, build something. Or yes, okay, if somebody builds something, yes, okay, you may come and, okay, just give it, okay, as a flying kick and destroy it. Or break it down, right? Clear. But when we say constructing, what is it that we are doing? We're putting the things together, we are adding them up. Did that make sense? Whereas on the other hand, you say destructive, what is it going to happen? Yes, okay. When you say destruction, you're going to just, okay, take the things apart or separate them, or you can say, okay, destroy one of the towers that was just built on the castle, for instance. Did that make sense? So when we say constructive interference, guys, the simple thing is that, okay, yes, that we add. What do we add? The amplitudes of the sound waves. So what do we get as a result of, okay, yes, constructive interference? Now, since we add things up, we're going to just, okay, get a, we can say, okay, yeah, final sound wave with a bigger amplitude than the components or component waves. Let me just go to another slide and we can look at this. So here we have, okay, there's a central line, just okay, tell us, okay. So again, yes, okay, we have our two waves. Or maybe it's a little bit close. Sorry. Let's just do it like this. This was our red wave, right? Clear? Okay. And we had a green wave. Okay. We can just make it, that's okay, smaller. It can be of the same amplitude, that doesn't matter. But that's okay, yes, okay, just to demonstrate it like how it goes. Now we mainly, as okay, you can say that, okay, as these two waves here is okay are in phase because it's okay that we had the peaks and the troughs at the same time. Did that make sense?
Yep.
Clear? Okay, so what were they were? In phase. Why? Because, okay, like things like this. Okay, although yes, okay, they have different amplitudes. But since they are in phase, that's mean yes, okay, going to mean that, okay, yes, that they will interfere. Okay, why would they interfere? Because it's more than two waves. Okay, so they will interfere. Or that's going to be okay, interference between these two waves here. But this interference here is going to be constructive. And what did we mean by constructive interference? That the red wave is going to be added to the green wave, or the green wave is going to be added to the red wave. And that will give us, okay, as our final wave. Which will be this one here. Did you guys get that?
Yes.
Here, or just as I said earlier, that, okay, yes, individual soldiers marching. What is it that they did? They stepwise, okay, at the ground at the same time. Clear? That's in phase. But the ultimate sound that you hear is mainly as, okay, just the sum of all those footsteps hitting the ground at the same time that are being added up. Did that make any sense? Okay, so what we get as a result of constructive interference is that, okay, yes, the amplitude of the final sound wave is going to be greater than the individual components. Clear? Okay, what were our individual components here? Yes, okay, the red and light green wave, right? Okay, but adding those up gives us, okay, yes, this bigger wave here, which is the brown wave. Clear? Did you guys get that?
Yep.
Now, does anybody have any questions?
Nope.
Okay. So please, guys, construct this. Okay, construct interference. What do you need? Well, okay, you need at least 2 sound waves. Okay, but the next requirement is that those sound waves have to be in phase. And what you get as a result of constructive interference is that, okay, as the resulting wave or the final wave is going to just, okay, be greater than the components. Practically, it's okay, they're just going to be added up. Okay, so if we said here is okay that the red wave, for instance, okay, had the red was 4, green was 3, for instance. Okay, then we can make this as, okay, brown has to be 7, because okay, these 2 fellows here were added up to give us the final wave.
I have a question.
Yes, my dear.
So does this occur at the first point where like the interference is?
No, it's going to be throughout, if that's what you're asking about.
And so does it
So
create
even here, it's okay. Even at these points, it's okay. Because okay, they will be as okay in phase.
So
Because
does
it's
it
okay.
create a third wave or is it just two of
No,
them?
this is just going to be your final wave, my dear.
Thank you.
Clear? Okay, and that's why I says okay. That's why I says okay. An easy way to yes, okay, understand construction is that okay, yes, you add up the components to get a final product. Did you get that?
So at the end, you'd just be left with the brown wave.
Exactly. That's going to be the final sound that you will feel or hear. Okay. Did you get that? Okay. Oh, yes, okay. People singing in the same group or people singing in a group. Okay, now some of them may be less louder than others. But okay, yes. But if they sang in phase, let's put it this way. The final sound that you get is greater than the individual sound that each of the singers produce. Did that make any sense? Clear? Okay. But this only happens when, yes, okay, you are in phase. What did we mean by being in phase? Practically, yes, okay, just when the peaks are at the same time and troughs are at the same time. Any last words? So, yes. What was the other kind of interference that we had? Destructive interference. What was the minimum requirement for an interference to occur that we at least had 2 sound waves? Okay, but when is it that these 2 sound waves as okay traveling through a medium will undergo as okay destructive interference is going to as okay be when they were out phase? Okay, now if you guys are in doubt what we meant by being out phase, well, okay, yes, here were 2 examples of sound waves being out phase. Did that make sense?
Yep.
Good. Okay. We did that. Okay. So let's see. So let's say it's okay. Destructive interference. Now let's take one example first. And let's say it's okay. We have our two favorite color waves as well. Okay. So we have a red wave, and we have it's okay the green wave. And what was needed for them to be as okay to undergo as okay destructive interference was that they have to be out phase. What does it mean to be out phase? That okay, yes, we don't have the peaks and troughs at the same time. Clear? Okay. Now we may say it's okay here. This is where there's interference. Yes, it's okay. This is where there's interference. Here there's interference. And let's say it's okay here, that's where there is interference. Yeah, okay. Now, guys, when we say it's okay, destructive interference, the bottom line is you had a red wave, you had a green wave. And okay, yes, they interfere destructively because they're out phase. And that's going to give us, okay, yes, this final wave here. Which we may say as okay, or B. So say it's okay, something like this. Did that make sense? So what mainly happens is that, okay, we can mainly say it's okay that here, sorry, destructive interference is because it's okay, the green wave was subtracted out of the red wave, which gave us, okay, yes, this final component wave here. Okay, or as we can say, it's okay that constructive interference, first of all, it's okay. It will only happen when waves are out phase. Okay, well, what do it's okay? What can we say? Okay, how do we define destructive interference? Is that when the final wave, or you can say even as okay, the sound wave is lesser than is okay one of the component waves. Whereas in constructive interference, what we mainly said was that okay, yes, the final wave is going to be greater than either of the component waves because they're added up.
Can you go back to the previous slide?
Yep,
Can you go back to the previous slide?
this one.
Yeah, thank you.
So we can mean it's okay, just if you want to put numbers into it, you can say it's okay. Let's just say that okay, yes, green was 4, or okay, red was 4, You can say it's okay, green was 2. Then okay, yes, blue was 2 as well. Whichever way went. Okay.
Can you just repeat the words at the top?
Here, destructive interference is going to be as okay when the final wave. What was our final wave? It's okay, the dark blue one, right? Okay. Right, okay. A small or a lesser. You can say it's okay, have a lesser amplitude. Or it's going to be as okay, smaller than one of the component waves. Okay, what are our component waves here? Well, okay, yes. The red one is a component wave. And okay, yes, the dark green wave, or the green wave is a component wave.
Thank you.
Okay. But guys, it is not more complicated than simple addition and subtraction. Clear? Okay, so when do we have addition? When we put things together, right? What do you call that? Putting things together. If you're Bob the Builder,
Constructive.
construction. Clear? Okay. And another way is okay. If you want to undo, yes, okay, the job that you just built. Destruction. Clear? Okay. Why would you say it's okay? Okay, construction is good. Well, okay, because that's okay. Everything was in phase. Clear? What did it mean to be in phase? Well, okay, yes, that's going to be as okay a form of interference. Or that's going to yes, okay mean yes, okay. Determine yes, okay whether the waves had their peaks and troughs at the same time. Okay, then they will be in phase. Whereas if the peak of one way and the peak of another way and the peak of another way, yes, okay, happens at different times, that's going to be out phase. Likewise, it's okay if the troughs of this, okay, the respective waves that we had happened at different times, yes, okay, they will be out phase. So for in-phase waves, you will have constructive interference, where you just add them up. Whereas for out phase waves, you will have destructive interference, where you may, it's okay, just subtract. And when you add things up, what is the final product going to be? It's going to be greater than the components. You had 5 candies, and you put 4 more candies into the ball, then you put 3 more candies into the ball. That's when you add up. What are you going to end up with? 5 plus 3 is 8, plus 4 is 12. So you end up with 12 candies, right? So the total number of candies is now 12. But that's only as okay when you have in-phase waves. Yeah. And that's why we call it as okay constructive interference. Whereas okay, yes, if there's out-phase waves, well, okay, yes. Some people may come and yes, okay, put candies into that ball, basket, container, whatsoever. Some people may come and take candies out of that, right? Okay. So they're not doing the same thing at the same time. So that'll be destructive interference, right? Somebody added 12 candies into that bucket, a basket. Somebody came and took out 4 candies. What are you left with? Only 8 candies, right? Why? Because, okay, somebody did some activity at one time and somebody did the exact opposite. Or that's okay, something which was different. Did that make any sense?
Yeah.
So what are you left with? Yes, okay, less number of candies, then okay, yes. Primary has okay, the first person who adds, the person who add 12 candies into here comes. What happened here? Did that make sense? Okay, guys, now a weird example. Okay. Or we can put it this way. Because, okay, what we said here, okay, yes, well, okay, yes, an example like this. Clear? Okay. We can even, yes, okay, go to another type of, yes, okay. Let's say, yes, okay, destructive interference like this. And we can say, yes, okay, our 2 favorite color waves, right? Okay. Well, okay, yes. That's okay, 1.5 cycle of a red wave. Let's say it's okay, something like this. Okay, let me just undo this one. Now, even these 2 waves here is okay, are out phase, right? Right? Yeah, now since they are out phase, what is it going to happen? Yes, okay, there will be destructive interference, and we has say that there's going to be destructive interference, okay. We're going to, yes, okay, subtract 1 wave from the other. And in this instance, yes, okay, this is going to be our final wave. So you will see, yes, okay, the final wave is going to be, yes, okay, lesser than the red wave, which was the wave with the greatest amplitude, right? Okay. Okay, where okay, yes. This fellow here is okay, means okay, we'll just subtract it out. So it can mean it's okay, all this was taken out of the red wave here and gave us this wave. Here, okay. This AV here, for instance, was taken out of the red wave from here and gave us this blue wave. Right? And this was taken out from the red wave here and gave us this. But yes, okay, in this case, yes, okay, what we still saw was that, okay, yes, the red wave, yes, okay, he or she was greater than the green wave. Where we at least for with surety can say that, okay, yes, the blue wave, sorry, is going to be, yes, okay, is also going to be, yes, okay, lesser than the red wave. Or let's just do a comparison between the blue and the red. And the red wave is still going to be, yes, okay, bigger than the final wave. Did you guys get that?
Yes.
Okay. But another thing that we also could see here is, okay, this is okay, these waves here is, okay, were completely out phase. Now, another example, guys, can be, let me just go to another slide. For instance, okay, we have two waves, and it's okay, we are going to, it's okay, say we have our red wave here. That's the red wave. And that's going to be, it's okay, our green wave.
Can I ask a quick question, or I can wait?
Just a second, my dear.
Okay.
Okay, you can ask it unless you may forget it.
Okay. So I know like we're just doing examples with two waves, but like hypothetically there could be 3 or 4 or 5.
Exactly. That's why I said in the beginning,
Right. So
two
then
or more than two waves. So there's no upper limits.
right. So then but the end result, so like the blue wave you've been like there'd just be like one wave at the end, right?
Exactly. Exactly.
Okay. Thank you.
That's what you get as a result of interference. Clear?
Yep.
Good. Okay. Okay. But that interference is going to, yes, okay, be determined on whether the waves that you had, 2, 3, 30, 400, whatsoever, were in phase, or whether those waves were out phase. Clear? So if they are in phase, or where they are in phase, you will have constructive interference. Whereas where waves are out phase, you will have destructive interference. Did you get that, my dear?
Yep. Thank you.
Good. Okay, so what is that we see here? Yes, okay, our two waves, the red wave and green wave, right? Okay. Now, I may not be as okay diagrammatically correct, but we can say it's okay where red wave has its peak. That's when green wave has its trough. Green wave has its peak, red wave has its trough. Yep. Okay, so what did that tell us? That, okay, these two bellies here, yes, okay, they are out phase. So what kind of SOK interference would that lead to? Destructive interference. Okay. Did you guys get that?
Yeah.
Good. Now, I know this is not a Mona Lisa, but if we say that, okay, yes, the amplitude of the red wave is equal to the amplitude of the green wave. Likewise over here is, okay, this and this. If the amplitudes were equal, then, okay, yes, hypothetically, this would be our final sound wave. no sound wave will be produced. Because they cancel out one another. So you can say, okay, there's total destruction of the two sound waves. Right. Just think of it in a, yes, okay, with our candy basket. Somebody has, okay, put 5 candies in that basket, and somebody has, okay, at the same time, has, okay, take those 5 candies out. What are you left with? What are you left with? That's okay. You'll be left with, yes, okay, 5 candies. Somebody's going to, yes, okay, get cavities. Right? So, but that's it. Yeah, okay. So, yes, okay, if equal, yes, okay, we can put it this way and say, yes, okay, if sound waves with equal amplitudes interfere destructively, no sound wave because they cancel out one another. Clear? So what was interference? Yes, okay, the event occurs where 2 waves or 2 or more waves meet at a specific point at a specific time. That event is called interference. Clear? Okay. What could be the nature of the waves? They could either be in phase or out phase. When they are in phase, what do you have? You have constructive interference. What's going to be the result of the constructive interference? That the waves add up. Or you can say, okay, the final wave is going to be greater than either of the component waves. There were 2, 3, 20, whatsoever numbers. Clear? Whereas on the other hand, we say, okay, destructive interference. What did we need for destructive interference? Is okay, first of all, we need interference. What do we need for interference? 2 or more than 2 waves. But for the destructive interference to happen, yes, okay, those sound waves need to be out phase. Did that make sense? Clear? Now, what do you mean? Okay, what's going to happen during a destructive interference? You can mainly say, okay, that the amplitude is okay. You can say, okay, the volume of one sound is going to just, okay, cancel out some of the other one. But what you get as a result of that is, okay, that the final wave or the final sound is going to be as, okay, lesser than either of the 2 component or either of the component waves. Did that make sense? Whereas, okay, if we went on this, guess, okay, extreme destructive interference, you can say it's, okay, 2 waves which are completely out phase. Okay, what can we mean by that? Okay, being completely out phase? So, okay, when one wave has its peak, the other one has its trough, and vice versa. Okay, okay. But when they have equal amplitudes, the peak of the one wave is going to get canceled by the trough of the other. Which are equal. So that's why it says, okay, 5 candies are being put into that basket at the other side. somebody just taking out those 5 candies. You're left with 0 candies. So no sound. Clear. Now, guys, this is still your basics. Although this chapter here is not talking as the name of this chapter here was not basics, but this is still going to be SOK basics. And these things are going to SOK, or we can say SOK, especially when we talk interference, is going to SOK be brought up again in a later chapter. Most likely, SOK, by the time we read that chapter, you guys might have, not might, you have forgotten everything about interference. So what is it I'm going to do to SOK refresh your memory? Was my tool or my weapon in my arsenal that I can use to refresh your memory?
Estes on it?
Huh?
Estes on it? I
If
don't
that's
know.
going to be the case, my dear, then you have 5 tests every day.
Oh, every day? My bad.
Then why not just, that's okay, bring your sleeping bag and just stay at school. Now, I'll be asking you guys about it, right? Okay. Maybe you guys can prove me wrong and say, ha ha ha, Mike, you told that we are going to be forgetting about it. You still remember, yes, okay, what interference is. Okay, then I owe you guys something. So if I owe you something, what are you going to ask for?
Extra points.
Extra points.
Yeah, plus 10.
Okay, and what if you don't know it then?
Oh well.
Okay, well,
Nothing happens because it's a learning.
the intent is to ensure that, okay, yes, your guys' memories is being refreshed from time to time, okay? Okay. I have no joy. Please, guys, don't think so. I have no joy in asking a question and it's okay, just putting you, yes, okay, you guys in the hot seat. Okay. Well, that's okay. I know because it's okay. Me myself, it's okay, read this book here once. Do you think you will be able to understand it by it's okay just going it over once? Okay. So that's okay. That's why it's okay. We may, it's okay, have to come back to chapter 2, although it's okay, we are in chapter 12. Because it's okay. Our chapter, whichever chapter it is. But it's okay. It will be brought up again. So right now, it's okay, guys. We are still in the basics. But with that said, guys, what do you think of physics so far? Anybody?
Not
Is
my
that a crime?
favorite.
It's not the worst.
It's
Not the
not the
worst.
worst.
Not my favorite at all.
Okay. Oops. Okay. So somebody said not the worst. Let's see for how long that will last. No. Okay, guys. Okay. Well, my thing, okay, let me just try to make it okay less difficult than it is. So For constructor interference, what do you have? What's a must? In-phase waves. For destructor interference, all-phase waves. Okay. What's going to be as okay? The end result of constructor interference, a final or a sound wave is going to be greater than either of the component waves, whatever number that was, 2, 3, 5, 8, 17, 20, 2000. Doesn't really matter. Okay. What do you get as a result of destructor interference? That the final wave is going to be as okay, lesser than either of the components. Or as okay, sound waves that had interfered. Did you guys get that? Good. Do you guys want to take the last topic of this chapter here? We're still in interference. Or somebody wants to interfere. No. Okay, guys. And to be more honest, that's okay with me. That's okay when we talk of ultrasounds. This is most likely going to be as okay the kind of interference that is just okay we may be ending up talking about. So that's going to be as okay where it says okay interference of waves. Now to be specific, yes, okay, for our subject, yes, okay, what do we mean by waves? That's okay, we will try you say it's okay, that's going to be sound waves. Clear? Okay. But what these sound waves here now are going to have is width, so different frequencies. Did you guys get that? Now, what did we mean by frequencies? Algebra says, okay, the number of cycles per second. Did you guys get that?
Yep.
Good. So let's just do it this way, guys. Say that, okay, this line here. Measure just, okay, the time span of 1 second. Did that make sense? Okay. Now, what are we going to have here? Well, okay, yes, they're going to be as okay, sound waves. With different frequencies, we mainly remit that the sound waves that we have as okay, that are going to be as okay, traveling in the medium here, are going to as okay, have different number of cycles per second. So let's just take as okay our two favorite colors for the sound waves and say as okay, here is our red wave. This is our red wave. Did that make sense? Okay, so we can actually just count the cycles like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's going to be 11 cycles in 1 second. And that's going to be the frequency of this cycle of our red sound wave. Did you guys get that? Yep. Now another thing that we can say is now we're going to have another wave, which is going to be our green wave. Yeah, and let's just do it this way. Okay, now don't go that much into the amplitudes, but anyways. So we can make this that we have 1, 2, 3, 4. That's 5 cycles. Completed in that 1 second, right? Okay, so that's going to be the frequency of the green wave. Did you guys get that?
Yep.
Good. Okay. Now, what is it that we may see here happening is that at some points, yes, we can say that our waves may be out phase. Clear? Clear? At some point, they may be out phase. We can say, we actually managed to say, that was going to also be one point where they were in phase. Or you can see in phase. Like that. Or you can here the last is in phase. Clear? Okay. So yes, at some point is it that the waves are going to be in phase, at some points is it that they're going to be out phase. Clear? So what do we have when they're out phase? What is going to happen? That will lead to destructive interference at those points. Did that make sense?
Yeah.
Whereas when the waves are in phase, the points where or two waves are in phase, that's going to lead to constructive interference. Yeah, okay, which made is okay. Now please don't catch me on the Mona Lisa point. Okay? But we can say it's our final wave maybe is something like this, for instance. Where we can say let's just do it. That they were bigger, yes, where we had or points, yes, where our two waves had constructive interference or constructive interfering because they were in phase. Whereas yes, at other points were just be lesser than either of the two waves because of destructive interference. Yeah, okay. But what caused that, okay, as these two waves here, is okay, at some points will constructively interfere, and at some points, okay, where destructively interfere was mainly because, okay, one wave was completing 11 cycles in a minute, and another was completing, it's okay, a different number of cycles per minute. Or let us put it this way. Two people are clapping. Let's put it this way. Yeah, okay. One person, yes, okay, make, let's say, yes, okay, 10 claps per second. Clear? Another makes, yes, okay, just 5 claps per second. What's going to happen? In that 1 second, there are going to be times there's only the one who clapped 10 times is going to be clapping, whereas the other one is not. But there's also going to be times where both of these people, yes, okay, will clap at the same time. Did that make sense? Okay, so when they clap at the same time, yes, okay, that's going to be, yes, okay, where you have constructive interference of these two people clapping. Okay, she's into that too?
Yes.
I hope she becomes the future dentist so she can, that's okay, do with our cavities that we get from eating those 5 candies that we took out of the basket. Okay, okay, but yes, okay, you can see as okay, if some people is as okay, if some person is okay, one was clapping 10 times in a second, another clapping at 5 times a second, there are going to be as okay times where only the 10 times per second person will be clapping. That will be destructive interference. Whereas okay, when they both clap at the same time because of different frequencies, that will be destructive constructive interference. Did you guys get that? So here is okay, due to is okay, the different frequencies, both constructive and destructive interference will happen. What do we mean by frequencies? Numbers that a certain event occurs in a unit of time. You can take any activity, clapping, stamping your feet, or whatever things you can do when you're happy. If I say yay once a minute, and so you guys only say yay once every 10 minutes. There's only going to be every 10 minutes that is okay, we will be in phase, right? So what happens when we are in phase? Constructive interference. For those 9 minutes where I just, okay, I'm the only one saying yay, I'd be alone. or you guys maybe just shit, and that's going to just, okay, destructively interfere my ye. Yeah, okay. And then it's just a matter of, okay, yes, is the ye louder than, yes, okay, you guys mumbling or saying S hit? Well, okay, we can always just, okay, get into that kind of match. But that's how it's going to be. So yes, okay, this was the end of chapter 2. Can somebody say a yay with me?
Yay.
Okay. Good. Okay, guys. So end of chapter. What do we have? Questions.
Can you just put the last slide up? I just want to make sure I have everything.
Well, okay, my last slide is probably not a Mona Lisa.
That's okay.
Okay, but my dear is okay, even if you read in your text, just read the last sentence, my dear.
Okay.
Okay, because what the main is, okay, just say here is, okay, therefore, okay, but when frequencies of waves differ, what did I mean? That the waves have different frequencies, okay? Both constructive and destructive interference occurs. So that's going to be as okay where you will have both constructive and destructive. Why do you have both constructive and destructive? Because, okay, due to different frequencies, as okay, there are going to be times where these two waves here were going to be in phase. And there are going to be times where these two waves here are going to be out phase.
Got it. Thank you.
Did that make sense?
Yep.
Okay. So you may, yes, okay, may see, yes, okay, the pattern of that in, okay, yes, question, yes, okay, figure 28.2 or 2.8, sorry. Okay. So if you look at that, what do you see? That, okay, yes. It goes like this. So what can you say happened here? At this level here. Let's choose a more evident color. At this point here. That one means, okay, those two waves were in phase because you had constructive interference, right? Clear? Okay. Where what you can say is, okay, happened, and let's say it's okay. These points here is that, okay, as the whatever waves we had were out phase. Did that make sense?
Yeah.
Okay. And when they're out phase, that's okay. What are you going to have? That's okay, destructive interference. So that's why it's okay. The final wave is going to be it's okay, smaller or lesser, or lesser in amplitude, or smaller than either of the component waves. Whereas when you have waves that are in phase, that's okay. They're going to add up constructive interference and make okay as a wave which is going to be bigger than the either of the component waves. Yeah, okay. So figure 2.8, where you see that okay, those waves are narrowed down. That's because they were out phase and you had destructive interference. Whereas okay, as where they are broader or bigger, that's because the waves are in phase and you had constructive interference. Did that make sense? Okay. And it's automatic because it's okay. One wave might have completed, it's okay, only 5 cycles per second. The other may have completed, let's say it's okay, 15 cycles per second or whatever. Yeah, okay. Okay, guys, now take your lunch break. And then, yes, okay, what you guys will have, so it's going to be, it's okay, a short lunch break for you guys, sorry. You have, it's okay, 16 questions at the end of the chapter to answer. And if you're done with those, then let's see. Yes. Then at the end of the book, from question 23 to question 49, which is from page 427 to 432. Yeah. So when do you guys want me to be back with you? Oops, that's some pretty bad destructive interference. Can somebody please say something? It doesn't matter with the frequency and things like that.
110. Is that a long time? You told me to say something.
Okay,
It's a lot of questions.
okay, 1 and 110. So make it 105. Okay, girls. Oh, guys, sorry. Go on, sorry. Okay, see you guys then. Now, did everybody do the questions at the end of the chapter? Okay. Any questions that had any issues? Any questions that you felt, oh, shit, what are they asking about? Or how did they get to that answer? No? So you guys are good? Okay. You guys done, let's just go to the back. Have anybody tried or started with the questions on the back? Okay. Any questions about those? Or you haven't come across anything yet?
No.
Okay. Well, anyway, let's look. Okay. So that's okay. I guess the first 4 questions in the exam review, or okay, test review, sorry, or chapter review, are in context to our related okay, diagrams A, B, C, D, and E. Yeah, okay, what I mean is, okay, just asked, okay, what best describe what is happening between A and B. Now, A and B, yes, okay, they are out phase. And that's why they will interfere destructively. Clear? B and C, they are in phase and they will interfere constructively. A and C. Now, guys, if B and C were constructive as in phase, and A and B were out phase, that makes A and C out phase as well, which may mean that they will interfere destructively, right? Okay. And okay, as D and E. Now they are in phase and they will interfere constructively. Okay, what do waves transfer from one location to another? Okay, that would be energy. Okay, so we can make this, okay, say some energies, not all kind of energies, but some energies as okay may transfer, or we can say it's okay, yeah, using waves to transfer, okay. There are some energies which doesn't require waves, but at least what we can say is okay, but all waves will do when they move from one location to another is that they transfer energy. Okay, example of energies that use waves: sound, light, and so on. Now, guys, which of the following best describes a sound wave? A series of contractions and rarefactions. Okay, waves that are heard by a man. Not necessarily. You do not hear the ultrasound waves. Why is okay, we'll get to that in the next chapter. Here, okay. So it's not going to be every sound that you necessarily will be able to hear. Movement of molecules and energy from one location to another. Well, that could be anything else but or anything else besides sound, right? Okay. Okay, waves that are used to make images of anatomy. Well, that's only applying for ultrasound, for X-ray waves and things like that. Okay. So here, that's what describes a sound wave is being as a series of compressions and rarefactions. Particles getting close and far apart. Right? Okay. Now, which of the following terms does not belong with others? So we have a list of terms where one is going to be be the black sheep. That doesn't belong in the group here. Compression. Region of high density. Region of high pressure. Or wide molecular spacing. Now, wide molecular spacing, that is rarefaction. And if you look at it, guys, now when you say yes, okay, compression. Because it's a certain area. Or let's say it's a certain volume in this case here. Of high density compared to, if that be the same volume, particles farther away. Okay, so here, high density, because more molecules per volume, or more or less, okay, mass per volume is you have that's okay, the molecules compressed and a region of high pressure. And the same again. An area. Okay, or we can say it's okay, the greater, as I say, it's okay, that's the greater the pressure from particle to particle, the greater faster will be the transfer of energy. So the only one that is yes, okay, not matching is okay, the terms here is going to be that they're going to be wide molecular spacing like we have here. Yeah, okay, so they are giving us a list of say yes, okay, rarefaction, region of low density, region of low pressure, and narrow molecular spacing. The narrow molecular spacing would have been the one that would be not belonging to those, because that narrow molecular spacing would have been compression. Okay, whereas okay, we say low density or low pressure or rarefaction is okay, they will always okay mean the same. Clear? Question number 8. Variations in all of the following identify specific waves as acoustic waves except from. And that's going to be as okay, your parameters. Clear? Okay. So pressure was okay as a diagnostic or acoustic variable. So was density. Anyway, it's okay, your acoustic variables, which has okay included pressure and density and what do you call it? Okay, distance. Okay. Okay, and that variation, that's what we also is okay called, or varying is going to be what we also can call oscillation. Now, question number 9. Okay. All of the following yes, okay, are true of sound waves except from. Now, it's okay, are they acoustic? I told you guys that acoustic is meaning it's okay, just a word that means, sorry, it's going to be it's okay pertaining to sound. Do we have another word that also it's okay will mean the same as acoustic? Another word that means the same as acoustic.
Movement,
Huh?
movement,
No. Why
Isn't it-
movement? Pump it up.
Isn't it sound?
Okay, sound. But there's still another word that still will mean, or you can say, okay, pertaining to sound. Let me give you guys a hint. It starts with an S. It's a place of eatery. Now, I never eaten there, so I don't know what kind of food they serve, but never heard of it? Okay, now have you, none of you ever heard of the thing called sonic? What does sonic mean? Son is sound. Ick is just pertaining to. So acoustic mainly as okay, just means the same as sonic, which means the same as sound or pertaining to sound, right? So what could you call it? Ultrasonic, ultrasound. It could also be called an ultrasonic exam, right? Did you guys get that? Good. So are sound waves acoustic? Yes, but if I say are they sonic? Are sound waves sonic? Please, guys, produce some sound. Produce some sound.
Yes.
Yes, they are. Good. Okay. They are pressure waves. Yes, okay, they are. Because, okay, pressure is one of the OMG.
Thickness parameters? No.
No, not bigness parameters, my dear. Pressure is one of the
Acoustic variables.
acoustic variables. Okay. They are transfers. Were your sound wave transfers waves? No, they were not. Okay. Clear. Okay. They move energy. Do they carry energy? Do sound wave carry energy?
Yeah.
Yes. Because sound was a form of energy, right? Okay, so anything which is a form of energy is okay, will carry energy. So the only one that didn't make sense here was transverse waves, right? Okay. Clear. What kind of wave is it that your sound wave were?
Longitudinal.
Longitudinal. Okay, good. Okay, all of the following are acoustic parameters except from. So you have, okay, as a list of 4 things here. Pressure, period, propagation speed, and frequency. And 3 of these are acoustic parameters, one of them is not. And that one that is not an acoustic parameter is pressure, because that was an acoustic variable. Period was an acoustic parameter, propagation speed was an acoustic parameter, and frequency was an acoustic parameter. Okay. Okay. 4 other SOK acoustic parameters were the wavelength, the amplitude, the power, and intensity. Those were the other 4 acoustic parameters which were not mentioned here. But pressure is not an acoustic parameter, it's an acoustic variable. Okay. Clearo, Miro, Badiro. Question 11. Which are the following best described sound waves? Now, what do we have? Yes, okay. Are they transfers? Are sound wave transfers waves? No, so that's how you can directly, yes, okay, exclude A as an apple and B as in boy. Those options are directly, yes, okay, eliminated. So now you're just left with 2. Longitudinal out phase waves. No, because we just said that, okay, sound waves can be in phase as well, right? Okay. Clear? Okay. Now, what are you going to do if you only have one sound wave? Okay, then it can't be out phase because there's only one sound wave. Clear? Okay, so that's okay. They are longitudinal and pressure waves. Why pressure waves? That's okay because pressure was one of the acoustic parameters. Not sorry, parameters, sorry. Variables. Clear? Okay, so what these variables pretty much okay here this specify is that just okay every sound wave is going to be made up of pressure, density, and distance of particle motion. So that's like you will say it's okay every human being most likely it's okay, or adult, let's put it this way, adult normal human being is okay will be standing up, having a head with 2 eyes, 2 ears, a nose, a mouth, 2 arms, with 2 hands, 5 fingers each, 2 legs, with 2 feet with 5 toes each. Okay, that's if you see something like that, that's okay. Entering a room, or that's okay. You say, okay, here comes a human being. Yeah, okay, but the parameters of that human being is then going to be as okay. Is he or she tall? Is he or she that's okay, whatever color? Black, white, brown, yellow, purple, rainbow color, whatever. Clear, okay? Things like that, okay. Is he or she thin, thick, fat, obese, or that's okay, anorexic, whichever. Clear? Okay. So that's going to say it's okay. You can say it's okay, specify as okay that characteristic of that specific human being. Okay, so that's going to be as okay with help of parameters. Did you guys get that? Okay, but every sound wave is going to just okay have your 3 acoustic variables: pressure, density, and distance of particle motion. Okay, guys. So longitudinal, right? Okay, they were longitudinal wave. What did it mean to be longitudinal? Somebody haven't been producing any noise or sound yet lately. And that'll be Dr. Angelis. What do you mean by a longitudinal wave? Oops.
I don't
Okay.
know. I can't remember. I just know that sound wave is longitudinal,
Okay.
but I don't remember why.
Okay. You don't remember why. Okay. Maybe Lillian can just refresh your memory.
Because it goes like to and fro instead of like up and down, right?
No, not necessarily, my dear.
The particles move in the same direction the wave moves.
Exactly. Whereas transverse, the particle motion, and the more the direction of the wave traveling was across one another. That's why we call it transverse. Or it's okay, they make a cross. The direction in which the particles move and the direction in which the wave moves or travels are across one another. Yeah, okay. Whereas now, yes, okay, the sound particles, okay, the particles move like this as I'm talking. And it's okay, the sound is going to travel like this. That makes it longitudinal. Okay. So along, or yes, okay, you can say in the same direction as the particle motion. So the only yes, okay, one that explains yes, okay, your sound wave here was the that they were longitudinal and pressure waves. Now, guys, let's look at this one here. 2 waves travel in a medium and arrive at a location at the same time. What events takes place? interference. Clear? Okay. Now, some of you will say, why isn't it a constructive interference? Why isn't it destructive interference? Because it doesn't say whether those waves are in phase or out phase. Clear? Okay. To know whether that was constructive interference or destructive interference, you will need to know whether the waves were in phase or out phase. It's not specified here in this question. It just says, okay, the two waves are traveling in the medium and reach at a point, or reach to a point at the same time. So that's what you need for interference. It could be constructive, it could be destructive. Yep. Okay, guys, question number 13. Unlucky number. Maybe I should take question 13 out of your answers or tests. So we go straight from 12 to 14.
We can take the points from 13 though. Just like free points for good luck. Thank you.
Can we do it this way? Yes, okay. I say, okay, no matter how you answer question 13, you get to go into points. Okay. What do you think I am?
A very nice man that wants us to do well.
I want all of you to do well. Okay, no, just kidding. Okay, first you should ask the author of this book to take, yes, okay, chapter 13 out. What is chapter 13? I may say something stupid. And if we take that chapter out, we may not be left with anything. Whoopsie. Yeah, okay. We can't. Because if we do that, then okay, yes, we are doomed. Okay. Okay. What type of waves will exhibit constructive interference and destructive interference? Our last topic. So those were waves with different frequencies. That is okay. Exhibit both constructive and destructive interference, right? Clear? Please, guys, it's not waves with different amplitudes. You can have waves with different amplitudes with same frequencies. Okay. Which can just okay. Still, yes, okay, exhibit. It could be either constructive or destructive. So here it says both. It's going to just okay, be both there. Okay, so that's why I say constructive and destructive. Okay, guys. Had it said destructive only, then what would be the answer then? What would have been the answer if they had said, okay, destructive interference?
Out of phase.
Our phase, right? Exactly. Very good. Right. Okay, our phase. Okay. Now, what unit or what units are used to report pressure of a sound beam? Now, don't get into that's okay, the sound beam thing. What they made is okay, just ask yes, okay, what is the unit to express pressure? So, what was the unit for pressure? Pounds is not a unit of pressure. If that's a unit of pressure, then okay, yes. US, okay, potatoes and tomatoes and bananas and whatsoever you buy by the pound, so it's going to just okay, be pressure, right? Okay. So pound, that will be a unit of what? Pound, it is a unit of what? Yes.
Wait.
No.
Mass.
Mass. Weight, my dear, is your gravity. I know. You says, okay, this thing is okay, weighs heavy. This thing here is okay, weighs light. But yes, okay, in terms of physics, pounds, ounces, kilograms, grams, so on, so yes, okay, it's all going to be units of mass. Okay. Centimeters. Now, why is centimeter not a unit of pressure?
Because it's distance.
It's a unit of distance. Right, okay, good, very good. Pascals, Uncle Pascal, is that a unit of pressure? The cheat here, guys, is pressure, Pascal, okay? And then we go as, okay, kilogram, centimeter. That's not a unit of, what you call it, pressure. Okay, clear? As a matter of fact, yes, okay, so far as we are concerned, it's not a unit of anything. Has a kilogram per centimeter cube, it would have been a unit of what?
Volume.
Had it said kilograms per centimeter cube,
Area.
Area.
no. Kilograms per centimeter cube would have been a unit of what?
Volume.
Nope. Kilograms per centimeter cube.
Density.
Your centimeter cube is a unit of volume. Okay, let me give you this. Okay, you're right on that one. But my question is, kilograms per centimeter cube is a unit of what? I can't even pick any of you guys here. Guys, what happened to what we call density?
Lily did say it. She did say it.
I didn't hear Lily say anything.
I think I talked over somebody at the same time, so I don't know.
Ah, okay. That will be density, right? Okay. Okay. That's okay. But centimeter cube, yes, okay. Those of you who said volume for that, yes, okay. But your answer was still wrong because I said kilograms per centimeter cube. Clear? Okay. Guys, you need to look more into your units. Okay? Because, okay, you may get questions, okay, where there is numerical calculation, you get the numbers right. But then you choose the answer with the wrong unit because you didn't know the correct unit. Okay? Just giving you a heads up of yes, okay, what can appear on your tests. Good. My favorite version. True or false? Now, for those of you who are new to my class or new to me, what does a statement need to do to yes, okay, be true? It has to be true from beginning to end. So if part of it is true and part of it is not true, then it becomes false. And if it's false from beginning to end, it is false. So true has to be true, the whole truth, and nothing but the truth. Clear? Did that make sense? Good. So let's see. True or false? Acoustic variables allows us to determine which waves are sound waves and which are not.
True.
True. Clear? Okay. Good. True or false? Acoustic parameters are used to describe features of sound waves. Features. Tall, short. Yellow, brown, green, whatever. So and so. Okay, guys, let's see how far we can get with the questions in the big black book. Question 23 on page 427. Yeah. What term is used to describe the effect of an ultrasound wave on a living tissue? Toxic effect? No, that will be as we talk about a poison. That will be a toxic effect, right? Or something else, okay, overdosed. Acoustic propagation of properties. Is that telling us, okay, that's the name for this, okay, this effect of sound wave upon the tissue? No, that was the other way around, right? Okay, biologic effects. Yes, that was the effect of the sound wave upon the tissue. Oh, yes, okay, the medium. Transmission properties. Okay. Yeah. Now, question 24. As a sound wave travels through a medium, what describes the effect of the medium upon the sound wave? That was your app, acoustic propagation property, right? Okay. How is it that the medium, or what's going to be, okay, the effects that the medium has on the sound wave? Okay. That big boom, yes, okay, may not reach your ears because you are so far away from it. Now, which of the following, question 25, which of the following is true of all waves? They travel through a medium. No, not necessarily. There are waves which are able to, yes, okay, travel in vacuums, right? Okay. Clear? Okay. So it may not apply to, yes, okay, sound wave, but here it's not just specifically talking of sound wave, it's talking about all waves. Okay. They carry energy from one side to another. Okay. The amplitudes does not change. No, like amplitudes will change. How and why? And so, yes, okay, we'll talk about that in chapter 3. More specific or more detailed in chapter 6. They travel in straight lines. It's not all waves that travel in a straight line. Sound wave does, but sound wave is not the only kind of waves that we have out there. Okay. Okay, what all waves have in common is that they carry energy. Just like sound waves. Okay, guys, which of the following types of waves do not require a medium to propagate? More than one answer may, okay. So which of the following waves, or which of the following do not require medium? So light, heat, and that's okay, television waves and travel in vacuum. Okay. So sound is the only one that won't be able to travel in a vacuum. But here they're not asking about, it's okay, which needs a medium. or which doesn't. Clear. Question 27. Which of the following characteristics, which of the following describe the characteristics of a sound wave? Now we can say, we have longitudinal, and then we have longitudinal. But we have longitudinal non-mechanical. That's out. Because your sound waves were mechanical. Why were they mechanical? Because they require motion of particles. Did that make sense? Clear? Okay. And yes, the ones that say transverse, yes, can't. All this, C says transfer and acoustic. But transfer waves cannot be acoustic, and acoustic waves cannot be transverse. Okay, so the only one that makes sense is that's mechanical, due to yes, that requires particle motion, and longitudinal. Right? Right, Dr. Angelis? Okay, do you mind tell us what longitudinal means?
When they move in the same direction as the
What
particles,
moves in the same direction?
the sound waves,
Okay, sound wave move in the same direction as what?
the particles.
As the particle motion. Exactly. Good. So you got that, right? Okay. You're probably never going to forget it. Question 28. Sound wave is best described as, yes, a series of compression and rarefactions. Well, yes, that does it. Transfer wave, yes, out of question. Okay, wave that a human can hear. Okay, or an oblique displacement of, yes, acoustic energy. It's not going to be an oblique displacement, it's going to be a straight displacement. Okay, so the only one that made sense here was series of compression and rarefactions. Please keep in mind, guys, it's not every sound wave that sound that we can hear. There are sounds that are produced which we don't hear. For instance, an ant walking on the floor. It produces sound, but we don't hear that. Oh, that's even that, and that's burps or farts. Okay. Question number 29. Now, all of the following are true about sound waves except from. Are they mechanical? Are sound waves mechanical waves? I don't hear any sound.
Yeah.
Yeah, okay, good. Okay, are they transfers? No. They carry energy from one place to another place, right? And they generally just travel in a straight line. So on the very first page of this chapter is we saw that. Yes, they're mechanical, they're longitudinal, and yes, they travel in a straight line, and that they carry energy. Okay, now here to me, yes, just give us a list of, yes, 8 things. And ask, are these acoustic variables? So frequency is not a variable, it's a parameter. Pressure is a variable. Propagation speed is not a variable, it's a parameter. mg. Okay, wavelength is not a variable, it's a parameter. Voltage has nothing to do with sound. It's electricity, right? Clear? Okay. Intensity is not a variable, it's a parameter. Usually people just, okay, confuse intensity and density. Usually people just, okay, confuse power and pressure. Clear? Motion of particle in the wave. Yes, okay. Yeah, should I be more specific and say, yes, okay, distance of motion. And density is a variable. Variable, sorry. Question, king. Now, what are the units of pressure measurement of an acoustic wave? Don't fall for the acoustic wave. That's just okay, confuse you. Okay. What the main is, okay, just ask you is, what's the pressure of, or what's the unit of pressure? So atmospheres. Yes. Now, when do you use atmospheres? To measure atmospheric pressure. Clear? Okay. And it's actually okay when that atmospheric pressure is greater than the pressure in your lungs. That air moves from the atmosphere into your lungs. If you remember respiration, I said that it's not the air, lungs expand and that pulls the air in, but rather the pressure falling in the lungs that sucks the air in. That was atmospheric pressure. Okay, something that pilots and people like that are very interested in. Okay, to ensure that, okay, that plane keeps flying. Pascals. Yes, Mr. Pascal. Yes. Millimeters per mercury. That's a unit of pressure as well. As a matter of fact, your blood pressure was measured using this unit here, right? And when we call it blood pressure, that's okay, it is a pressure. Did that make sense? Clear? Pounds per square inches. Now, why pounds? Because, okay, that would be a unit of force. Clear? Okay. Per square inch. Which will be a unit of area. Clear? Nextus, mextus, pretextus. Question 39. Sound wave can be characterized as energy moving through a vacuum. We already said that is Mission Impossible 16. A variable. No, not necessarily. Cyclical oscillation of certain variables. And that's your answer right there. Some of you may say, okay, where does it say that? The end of the first paragraph in your acoustic variables talks about it. Clear? Okay. A principle of acoustics. Okay, there can be many principles of an acoustics. That doesn't necessarily explain sound waves. Okay, maybe we can check the next 3 questions. Okay, so let's see. It's okay. Match the 3 acoustic variables, pressure, density, and particle motion with their correct units. More than one, yes, okay, may apply. So pressure, all going to be Pascal or any unit of force per unit of area, right? Yeah, so we have Pascal, that's the PE. Okay, and then we have, okay, yes, the unit of pressure in area, pound per square inch. Just as you had in the previous question, right? Okay. Density. Now, what we're going to make up density? Mass per
Volume.
Volume.
volume. And what will be a unit of volume?
Liters or any unit of distance cubed.
Exactly. Very good. Now we got that right. Yeah. Okay. So let's see. Pound per inch cube. That's one, right? Okay. And kilograms per meter cubed. Okay. Units of mass per units of area, volume, sorry. Particle motion or distance of particle motion, because that was our last acoustic variable, right? Clear? Okay. So that's just going to be as okay things such as miles, centimeters. Those are units of distance. And centigrade degrees and Fahrenheit degrees are just 2 ways of measuring the temperature. Now, I don't know about it's okay, what I haven't been out yet. But what's the temperature where you guys are?
Freezing.
Freezing. Good. Then I have a suggestion here. Stay indoors. Okay. Put some firewood in that fireplace, get a blanket, a cup of coffee, and okay, yes. Okay, yes. And your green book and read and enjoy. So, okay, guys, from question 43, yes, okay, we will start with that from tomorrow, okay? Okay. And because it's okay, you will see it's okay, these kind of questions, it's okay, popping up on your chests. Now, if anybody doesn't have a word of wisdom, then we can adjourn the class. Nope. Okay. Then see you guys tomorrow. It's Friday, right? Okay, good. And so far, that's okay. Our propagation speed is pretty good. So right now, yes, okay, we are in solids. Okay, that's right. Okay, guys. Take care then.
All right, see you tomorrow.
Okay, take care,
Bye.
guys. Okay, bye-bye. God bless.